Hey everyone, excited to be here, and yeah, I'm going to be talking about some of the things that we do at Luma AI, particularly when it comes to training large multimodal generative AI models. That's a mouthful, but I'm going to be trying to present some of the challenges that we face in scaling these massive models up. So first, a brief overview on the content. I'm going to be giving you a very brief overview on what we do at Luma, a brief overview on what we mean by multimodality and the background of that, and then I'm going to be going into some examples of challenges that we face in terms of efficiency and scaling for these large models. So our mission and our product directly is to build multimodal general intelligence that can understand, generate, and operate in the physical world, thereby enabling a new kind of intelligent creative partner. We recently, 2 weeks ago, we released Ray 3, which is our state-of-the-art generative video model. Think of something like Sora or VO from Google. It's kind of playing in the same ballpark. And this is our first model that is capable of thinking and reasoning, which is something that we're kind of inspired with from like the language modeling perspective. And it's also like the first model in the industry that can generate 16-bit HDR color, which is very nice for professional workflows, color grading, and people working on really cool creative projects. So this model specifically, we try to outline a couple things, like the fidelity is really good. We have HDR support. But some other thing where we have like heard a lot in the previous talks about is physics. Of course, this model is not like physically fully correct, but we see some really emergent behavior when we start training these large models with really well-designed data and model architectures where physically correct appearance and movement can emerge. Now, what do I mean by multimodality? So I just showed you some examples of a text-to-video model, and that can also be worked as an image-to-video model. But we're thinking a bit bigger than that. So, for example, there's modalities like videos, images, text, audio. And if you think a bit more, there could even be modalities like we've seen before, like simulation data or something that is more physically inspired. And the main difference between these modalities is some of them are like very long context if we think in terms of transformers. Some of them are short context like text. Some of the longer ones would be, for example, video. And from each of these modalities, we can see that these models learn something very different. For example, videos can give important spatiotemporal clues about environments and things. Images can help with composition, aesthetics, and scene understanding. Text is very important for like abstract reasoning and connecting between the dots. And audio can help with like personality of speakers, for example, of course, and also with like physical environments and spatial distance. And there's many more than that. And the work I'm focusing on at Luma is about scaling and efficiency. So trying to make sure we can train these models at thousands of GPUs, making sure we can run inference at scale in a distributed manner, making sure that all of these things are reliable and efficient. So let's look at some of these challenges specifically to these different types of modalities. So for example, in long context, let's say videos, we have a lot of different challenges, mostly limited by the compute that we are working with. So GPU memory is a big factor. For example, like long context activation memory usually tends to blow up very drastically. So we need sophisticated like parallelism schemes, making sure our algorithms are efficient. Then there's the thing of ON squared compute, particularly about the attention mechanism in most of the transformer architectures that we use every day, where we can see that like as we scale the context, attention starts to become the predominantly limiting factor. So we need to figure out how we can make that efficient in the long context case. So these kind of things are mostly compute bound as a result. Now, in the short context, for example, in LLMs, where we do next token prediction, so we like predict each token at a time, try to figure out what the next word is going to be. There's very different challenges in terms of like architecture and in terms of systems. So one particular thing is, given that we like generating one token at a time autoregressively, we need things like KV caching to prevent recomputation. And we need to be very, very careful about compute and communication overlap. So in the long context case, a lot of the time is spent in attention kernels. In short context case, this compute time is very short. So if you're like parallelizing your models, it might be the case that if you are doing computation and then you're doing communication, at the same time your GPU is kind of sitting idle, which I kind of like try to illustrate in the diagram on the right. So you need to be very careful about all the communication you're doing and make sure that it's as overlapped as possible. And these kind of situations are usually very latency bound. And then there's challenges about multimodality as a whole. So here on the right, I've tried to illustrate like an example of what a multimodal training batch could look like. You could have like interleaved text, video, audio, images, and all of these can have like different lengths, different challenges in terms of how you prepare the data, and can also have like different challenges in terms of how you interpret them in the model during training and during inference. So one big challenge is trying to figure out how we can unify our training and inference code, because we really don't want to like spin up 3 different things for all of the different modalities. At the same time, we need to have optimized kernels and optimized solutions for all of these cases. Like I showed before, for video, we might need a super optimized attention kernel, but for text, we might need a different solution that is just optimized for just the text-specific case. And the final thing here is also about data quality and processing. So each of these modalities needs to be handled very carefully in order to teach the model exactly what we want it to know. And the final thing I'm going to be chatting about here is scaling challenges. So this is about just making these training runs scale across thousands of GPUs and running inference in a distributed fashion across thousands of machines as well. So on the right here, I've illustrated like an example of how a model could be distributed across different GPUs, how optimizer states could be sharded, how communication buffers could be distributed. And this is very tricky to figure out how to fit everything into memory efficiently. And at the same time, like I've tried to illustrate here, if there's just one GPU in thousands of them that crashes because of an out of memory or that is slow for whatever reason, it takes down your whole run. So that is something that is very tricky to figure out. Also tying into that is data loading. If one GPU doesn't get fed data quickly enough, that's also taking down the run. And at the same time, there's also checkpointing. At this kind of scale, GPUs fail all the time. So anytime anything fails, we need to be able to resume relatively quickly. So yeah, this is like some example of the model we recently released that is quite nice in terms of fidelity, adherence, and physics. And we're trying to push the boundary of what can be done in multimodal Gen AI. So if you know anyone interested in solving that, we are hiring. And with that, I'm done. Happy to take any questions.
Questions?
So hello, thank you for the great talk. I know that you're a computer graphics person because you taught it to me. Now my question is it possible to perform conditional generation and conditioning on meshes and 3D scenes? Because I think this is a very interesting, would be a very interesting direction.
Yes, is a great question. And in fact, at Luma, we started out doing something very similar. We started out with 3D generation, 3D reconstruction, and all of these things, and slowly expanded our scope towards all of the different modalities. And absolutely, 3D can be one modality that these models can learn a lot from, like the consistency of space, and also like how 3D models or 3D things animate and things like that. And that is definitely possible with figuring out the right way of putting all of these modalities into the model. And that is something that the industry really hasn't solved yet. So this is a pretty deep research problem that we're trying to understand. And 3D can definitely be part of that.
One more, yes.
So your focus is mainly in this application where you create the video images, so you do not want to go into some real physics applications, or?
Is a great question. So currently, given the customers that we have and what we currently have been working with, our models are mostly used for creative work and these kind of things. So we're currently mostly trying to branch out from that and trying to expand on top of that. But there is definitely like potential for incorporating like physically based data, or like data that is actually mapping to the real world. Like if you imagine you have a fully unified multimodal architecture that can understand also like parts from physics, that can also like allow you to tie and bridge the gaps between things like text and physical data, or like images of simulations and physical simulation data and stuff like that. It's currently not something that we're like strongly focusing on, but it's definitely something that is interesting.
Perfect. Thank you so much, Thomas.